Welcome. Now I'm going to start the next name reactions related to carbohydrates, that is benzyl benzilic rearrangement. In benzyl benzilic rearrangement, what is the setup? Is that what is the substrates? How will you identify it that this is the benzyl benzilic rearrangement? What you see that if the two carbonyl groups like the CO and CO, they are adjacent to each other, and let's say here some other groups are there, then we understand that, and the medium should be the basic mediums, like we can say that OH or any basic mediums are there. Then we will understand that is and that is the basic mediums. Let's say NaOH is there like this. Then we understand that this is the benzyl benzilic rearrangement. And here that condition should be that condition is, since we know that this is the basic mediums, and here what we get that OH minus. Okay, and what we see that if OH is there, if any chance of in these substrates, if any acidic hydrogen is present, on that case it will not do the benzyl benzilic rearrangement. It will simply do the acid base reactions, because that acid base reaction is very fast reactions. Let's say if it is like this, CO and CO, I will understand that this is benzyl benzilic rearrangement. That is, the substrate should be two CO groups adjacent to each other, that should be present, means that two CO group is each in adjacent to each other. Then, and the condition is basic medium, then this is the benzyl benzilic rearrangements. Okay, now this is the same case that is there, but here what we have that, let's say CH2 CH3 is present. Then what will happen, let's say here some other groups is present, phenyl, and what will happen in this case, here what will happen that you know that this is CH2 and H. So this is the acidic hydrogens. This is the acidic hydrogens. Now if we have this medium, basic medium NaOH, this is going to give OH minus. So this OH minus, what will do that, this is act as base and it will abstract this acidic protons. And what will happen, that acid base reactions will happen. It means that pH, CO, CO and CH2 minus is there, plus what will be there, that is there pH, CO, CO and CH3 is there. So they will do that, get that acid base reactions, and here water will release. So some other reactions will happen. So what happened, that here condition is that there should not be no acidic protons. Okay, to avoid this type of acid base reactions. Condition is no acidic proton, no acidic proton should present. Okay, so no acidic proton like this group CO, here CO, and let's say here phenyl is there, here phenyl is there, here no acidic proton is there. So and if it is that basic mediums, let's say NaOH is there, then here that benzyl benzilic rearrangement will happen. Benzyl benzilic rearrangement. Okay, so what you have to memorize for this name reactions, benzyl benzilic rearrangement, that first thing is that the substrates should be that CO groups, they should be present in the adjacents, and medium should be the basics, and there should not be no any acidic protons in the substrate. No acidic protons should be present in the substrate. Okay, so if this is that, then that is going to give a benzyl benzilic rearrangement. Now we will look the mechanisms. After that we go to the shortcut how we will solve this question. So how the mechanism it will proceed. here if we have that CO groups and CO groups, let's say here I have that phenyl, let's say here I have the phenyl. Okay, no acidic proton is there. Now what I have that this basic medium is there. Then what will happen that this OH minus here, since no acidic proton is there, okay, here no acidic protons, so this will act as a nucleophile, because this can act both base and nucleophile. Okay, but since that no acidic proton is there, so it can't act as base, so it will act as a nucleophile. Okay, but if acidic proton is there, first is going to be act as acid base reaction, because acid base reaction is a fast reactions. Okay, so to avoid that, we should not have the acidic protons. And now this NaOH are act as a nucleophile. Then what will do that, it will, nucleophile means what it will do, it will attack to this electrophilic center, because here delta positive and this is delta negative, so this is attack to that electrophilic centers. Then what you will get here, this is going to pH, this is CO, and this is going to be O minus, and this is going to be the pH, and here we will form this OH. Okay, this negative charge is there, that is neutralized after that, then we are going to get this one OH. Now what will happen now this case, since this is a electrophilic center here is there, and so this pH will attack to this electrophilic center, because here again delta negative and delta positive is there, and here since here so since here electrophilic center is there, so here we know that OH minus is also present, but before attacking this OH minus to this electrophilic centers, this pH will attack to this center. Reason is that here we have that charge also there, negative charge, so some repulsions also will happen. So to avoid that, this pH will directly attack to this. Okay, so that is the things, because previously what happened that there is no any repulsions was there between these ONH, because they are the stabilized, but now it is getting negative charge and it is a pH. So what happened that this pH will attack with this, and this will going to be like this. So what we'll get here, that pH, this is going to CO minus, and this is going to be that C, and this is the O minus, and that has this had migrate, so this is positive charge, and this is going to be the OH. Okay, and this migrate here, that is pH. Now what will happen that this negative and positive bond means negative and positive, so that is going to be that CO minus. Here we have that pH, here we have that pH, and this is going to CO, and this is going to be that OH. Now what will happen that this negative charge here, this will attack to this proton, take this proton, and this is going to be negative charge here. So what will get here, that pH COH, and this is going to be the pH, and this is going to be the bond CO, and this is going to be that O minus. After protonations means that after work up, what will get that this will get H. It means that pH 3 double bond OH, and this is going to be the pH, and this is going to CO, and this is going to the OH. So this is the final product, okay, for this reaction. So this we will get after the doing this. Okay, so this is the mechanisms of this Benzil and Benzilic rearrangements. We know that this type of mechanisms, how we will get that after they will get the experimental results, they will do that how the theoretical may be. Okay, so this is the how this mechanism is proceeds. Okay, so what we get here, that no acidic proton should present, After that, this OH will act as nucleophile because there is no acidic protons, and this OH, but first this OH will attack here, then we'll get this negative charge, and then what happened that since here we are having the negative charge and OH minus is there, but it will not attack because this is present in the medium. But before attacking this OH minus, pH will attack. The reason is that here negative charge, so there is some repulsions between them, so that's why the pH will attack here, and this is the electrophilic centers. After that we will get here. Now this positive negative make bond, okay, and this negative charge take these protons. After that the negative charge, and this is work off, then we will get these products. This is the final product for this examples. Now we'll solve that more. So yeah, now we'll look that how we'll do the shortcuts. So what we get here, we have this pH, CO, pH is there. That if you do this, you can write pH, CO, pH, and if you have that basic medium, then what we'll get here, that is going to get pH. Here we get that OH, and here we have that pH, and here we have that CO and OH. That we get now. So how we'll remember, how we'll do the shortcut? Always no need to do this mechanisms. So we should because if you do the mechanism all the times, then it will take time. So there is a shortcuts that what we will do that in this case. Okay, this is the shortcut. How can you do that? So how will you do the shortcuts? This is very important because we always don't need to do the mechanism. So if we have that pH or any group CO and pH, and if we have that NaOH, okay, any groups, then what we will do that, make take one carbons, okay, because and one we know what we know that in one carbons we have to make that 4 bonds. So here what we'll do that, always take one carbons and one group will be the OH and other group will be the COOH. Okay, this is the first point. In this benzilic rearrangement, what we have to do that, one group will be the OH and other group will be the COH. This is the always for benzilic rearrangement. Benzilic rearrangement. So wherever you will see that benzil rearrangement, take one carbons and attach one OH and other side COH, and that two bonds are remaining. So one bond and one bond. So one bond is going to be that whatever this that this CO, in this CO, this is the first center. This is whatever that will be here, and other will be that this other CO groups is there. So that is going to be attached here. So this is the final product. That's what we seen here. In this case, you will get pH, OH, this is COH and pH. Okay, so this is the shortcut. What we will do that, first take one carbons and always OH and COH, because in one carbons we need to make the 4 bonds. One will be OH and on the other will be the COH, and remaining 2 bonds will be the in the CO whatever that groups were attached, pH and other say CO groups, what will attach, that will come here. Okay, so that is the final product for this question. So this is the very shortcut. We don't need to do the mechanisms all the times. Okay, so it will clear more while solving the examples. Let's say this groups. So what is there? So I don't know anything. What I will do that, take one carbons, one group will be always OH and other group will be always COH. Okay, now that 2 bonds are remaining. So what that in this carbons, okay, one group is this and other group is this. So what I'll do here, one groups I will take this one. Okay, one group side this is attached, and other groups that is going to attach like this one. Okay, and just name it if you get confused. 1 2 3 4 5 6. Okay, and this is, let's say, 7 8 9 10 11 and 12. Okay, so what we see in that, this is, let's say, 1 2 3 4 5 and 6, and this is 7 8 9 10 11 and 12. And what we have, that they have the group between 6 and 12. So 6 and 12 they were there, so join that 6 and 12. Okay, so this is the final answers. So as simple as it is. So what our duty is that whenever you see that this type of, here you see that no uh, acidic proton is there, because this one carbon is already attached to 1 2 3 and double bond is there. Okay, this is also 1 2 3 and double bond is there, so no acidic proton is there. If no acidic proton is there and medium is NOH, then what will take, what will do that, take one carbon, attach one side OH, other side COH, and whatever the groups that is attached to this CO and this CO atoms, whatever these groups and these groups, just doing that. Okay, that is the shortcut, that's all, for solving this Benzil and Benzilic rearrangements. Okay, we're moving to the next questions. You see here these examples. So what you see that here, any acidic proton is present. These questions here, acidic proton is present, right? Because in this CO, if we have that CH2, then this is going to be the acidic protons, because itself, then that is going to be stabilized by this. So acidic proton is there, so it will not do that Benzil Benzilic rearrangements. No Benzil Benzilic rearrangements, because here what we see that this hydrogen is there, and here two hydrogens are there. If two hydrogens is there, then this NOH, what it will do that this will obstruct this proton, this act as a base, and it will obstruct these protons, and what you get is this negative charge, and there will be some acid base reactions will happen here. Acid base reactions will happen. Okay, so we will solve more related to that Benzil Benzilic rearrangement in the next class. Today one example is fine, other we will solve in the next class. So this one also I have solved this one, that is pH and these groups. Here also no acidic proton, so remember that here CO pH, here no acidic proton is there. So if we have this NaOH, basic medium is there, then what will do that, our work is to take one carbons, and one will be OH and other will be the COH, and in this carbon atom what will be attached, that will be there, and other side this carbon atom what will be there, that will be this carbon. This is the final answers for this question. So likewise we will solve the questions related to Benzil Benzilic rearrangements. Okay, now moving to that next name reactions related to carbocation, that is Baeyer Villiger oxidations. This name reaction is also very important name reactions. Maximum times this name reactions is applied because with the reagents also that Baeyer-Villiger oxidations is used. So this is very important. So what we see here in this Baeyer-Villiger oxidations. So we have seen that if we have that aldehyde groups, if we have the aldehyde groups, and if you have the strong acids like KMNO or strong oxidizing reagent, then we will directly get that acid groups. Okay, but if you ask somebody that if you have the ketone group convert into a ester, then it is a very difficult that you can convert it, but it will take lot of times. So for that, what will happen that Baeyer-Villiger oxidations has come. So this Baeyer-Villiger oxidations, what it will do that from ketone groups to it will directly convert into the ester groups if you have the Baeyer-Villiger oxidations. Okay, like that Baeyer-Villiger oxidations also, if you have this aldehyde groups, and if you give that Baeyer-Villiger oxidations, this also convert into the acid. But this one we can also convert. This one we can convert also by using that strong oxidizing reagents. But this one that using strong oxidizing reagent, that it will very tough to convert. So here that Baeyer-Villiger oxidations has to be used. So that is the reasons why Baeyer-Villiger oxidations become very important, because if you have the ketone groups and from ketone groups you want to get the ester groups, on that case if you use the Baeyer-Villiger oxidation, then we will directly get the product of ester. By other than Baeyer-Villiger oxidation also you get, but that is very tough to get. So that's the reason that Baeyer-Villiger oxidations is used to convert ketone group into ester groups. Also, this Baeyer-Villiger oxidations also used in the conversions of if you have this diketones. This type diketones is there. Then also if you give that Baeyer-Villiger oxidations, then it will convert into these groups. This anhydrates group. Okay. So Baeyer-Villiger oxidations is used in this type reactions. First ketone group is there, then we can use Baeyer-Villiger oxidations. Baeyer-Villiger oxidations. And if aldehyde group is there and if you want to convert into acid, then also we can use Baeyer-Villiger oxidations and we can convert it. And if we have the diketones and you want to get that anhydrates groups, then also we can use the Baeyer-Villiger oxidations and we will get that anhydrate products. So this is the functions of the Baeyer-Villiger oxidations, means where we will use the Baeyer-Villiger oxidations to get that respective products. But it is mainly used to convert that ketone to ester groups, because for converting ketone to ester it is very tough other than Baeyer-Villiger oxidation. So Baeyer-Villiger oxidation is mainly used for conversion of ketone to the ester groups. Okay, so now for that, let's say if you have this ketone groups, sorry, this ketone group is there. Let's say this is the phenyl rings. So what is that? What is the reagent is there for conversations of this? So reagent is peroxide will be there. This is the very important. So what is the reagent we will use? That is peroxides. So peroxides, we know that peroxide means that double bond O, like this group is there. That is called the peroxides. So what are the peroxides that is used for this? What are the peroxides that are used in the Baeyer-Villiger oxidation? That can be that H2O2. You know that this is O and HH. Okay, that can be H2O2, and it can be that meta CpPba. This is maximum times this will be used. Maximum times. Meta CPPB means metachloroperbenzoic acid. It means that this is like this. Okay, here let's say if you have that metachloroperbenzoic acid, it means that here COOH is there. This is the perbenzoic acid, and to that this is ortho and this is meta. Here we have that chlorine. Then this is that. Okay, all right here. This is the perbenzoic acids. Okay, and here we have that chlorine. This is called that meta chloroperbenzoic acids, or that we can write simply meta CPBA. So the reagents can be H2O2 or can be that meta CPBA, or it can be that H2SO5. How it is? That is going to be that S double bond O here OH, and here we have that perbenzoic, means that is OH. Okay, so we see that 1 2 3 4 5 2 hydrogens. Okay, so this is also used, H2SO5. So perbenzoic acids can be meta CPPBA, or can be that H2SO5s, or sometimes that this also use Me3. That is Me3COH, MECO3H. Okay, this means that CH3, this CO, OH. Here also what we see that benzoic acid, that is paracids. So MECO3H, this is also used as the paracids in Baeyer-Villiger oxidations. So any of these reagents is given, either H2O2 will given, or meta CPPBA, or we have that H2SO pipes, or that is MECO3H. Okay, so any of this reagent is given, then we understand that this is the peracid, and if that ketone group is there, then we will convert it that into a ester groups, and that name reaction is called that Baeyer-Villiger oxidations. Okay, and what we know that for identifications, so if you get confused that whether this is peracid or not, so note that if any CO3 group is present, then more chance of peracid is there, more chance of peracid. So if you confuse it, then let's say that CO3, so this type of is there, then there is a chance of paracids. Here also you see that CO3, I'm not asking, so not CO3, lots O3. Okay, if O3 group is there, then understand that paracid is there. Okay, here also O pipe more than 3, it's fine. Okay, O pipe is there, so there is a chances of paracids. Here also O3 is there, O3, so there is a chances of paracids. Here also SO5 is there, so there is a chances O3 or more than 3 is there, O3, O4, O5, then chances of paracid is there. Okay, so this is the simply paracid, so here O3 is not there, but maximum times if you see that O3 is there, then there is a chances of paracid is present. So this is that basic things about of that Baeyer-Villiger oxidation. So what we see that ketone group and peracid is there, then we will do that Baeyer-Villiger oxidations. So what is the mechanisms? After that we will go for the shortcuts. So mechanisms of the Baeyer-Villiger oxidations. mechanisms. What we have that, let's say we have this ketone groups here, CH3, and we have that peroxides. So let's take which peroxide I will take. So any of this peroxide, any of this you will take that, take one. Okay, so I'm taking that to simplify. I'm taking that HOH. Okay, this one I take, or any of this one, or we can take, mainly our work is that here this peroxide work is important. Okay, or if I take that CH3CO OOH, then what will happen now? So this is the electrophilic centers. So before that, what happened that here since CH is there, so to increase the electrophilic center of these carbons, sometimes that one more reagent also may be given, because the reactions will happen very fast, means quick reactions will happen if you have that AgNO3. What is the work of AgNO3? This is going to give that Ag plus, and this is the Lewis acids. So Lewis acid is to that this will take the lone pair will give the lone pair electron, oxygen will give lone pair electrons to that Ag plus. After that, this will get that delta positive charge. Okay, then this will attract electrons toward itself. So here we get more delta positive charge. So that attacking of this group will be easy. Forward. Oh, sorry. I'm very sorry. Yes. So here what happened that these protons, this is a very acidic protons is there. So what I said that if HOH is there, then what will happen that this is the very acidic proton. So what will happen that this will release here, and this lone pair will attack uh, these acidic protons. Okay. Sometimes if it is not there like that, to increase these electrophilic centers, that's what I want to say, that if this group is there, okay, if this group is there, and let's say if we have that CH3, we want to increase this acidic so that the nucleophile will attack to this electrophilic center. We want to increase that electrophilic center of carbon. Then what we will do that first is like we can here, as here what we have the peroxides. Peroxide is there, so that peroxide will use, because this is the acidic protons. So if you have that HOH, then this is the acidic proton, and this lone pair will give here. It means that this H is there and this is going to share here. So this is going to get the positive charge, and if oxygen is more electronegativity than carbon and it is has positive charge, so it abstract electrons, so it will get that more positive charge carbon, so that nucleophile will easily attack here. So the increased electrophilic center of the carbons, either we have that peroxides, or we can give that AgNO3. This also do that same things, because this is also a Lewis acid, and that is also this lone pair of oxygen can give electrons to Ag, and then this will get the more positive charge. Or we have that any acid groups, any acids, like if you have that HCl, then also we are going to give that H plus, and this H plus is here come, then there you have the lone pair of electron give electron to this proton, and this carbon will get more electrophilic centers. So here we no need to take any reagents, because peroxide itself has the acidic proton. So this lone pair will attack to this acidic protons, and this oxygen will get the positive charge. So what will get here? So this, sorry, OCH3. Here that lone pair electrons were there. and that is, here we have that CH3, let's say CO, and we have O and O and H. So this lone pair electrons, what will happen, that this will abstract these protons, because this is the acidic protons, this is the acidic protons, and this is going to get here. So what you get now, CO, and here we have that CH3, and since this is attack the lone pair, so here we have that H, and lone pair electron is attacked to this proton, so this is going to get positive charge. And here what will have, that CH3, CO and O, and this is going to be the negative charge. Okay, now this is become a electrophilic center, this carbon will become a more electrophilic center, more electrophilic center. Then what will happen, because this oxygen will take electrons toward itself, so this is going to be more positive charge. So now it is act as a nucleophile, because the negative charge is there. So this peroxide, why we have taken that peroxide, acting as a to give that acidic proton, as well as it also act as a nucleophile. So both that peroxide is acting two things. It is acting to donating acidic protons to increase electrophilic center, to increase electrophilic center of carbon. This is the one work it is doing. Another work what it is doing, that, and this is act as a nucleophile. So both work is done by the peroxides. Okay, first it is acting as a donor of that acidic protons, and then it acting as a nucleophile. Now it will act as a nucleophile, and what it will do, that it will attack to that electrophilic centers. Okay, because nucleophile will attack to the electron deficient groups, and this is going to release here. So what we'll get now, this is going to be the O negatives, and here we have, let's say, CH3, and this has attack here, this one has attack here, so this is going to be that O and O, and this is going to be the CO CH3. Okay, this is what we get. Now what we seen here, here the repulsions will happen, because here also lone pair is there, lone pair is there. So here what will happen, that repulsions. So due to these repulsions, what will happen, that the next groups, okay, here the migratory group will be the migratory group will comes here, because here that this bond is going to break due to the repulsions. Okay, this bond break due to repulsions. So what will happen, that the migratory groups, okay, so the migratory group will comes here. So in this case, in this carbon, which is the more migratory groups, CH3 is there, phenyl is there, and this O will not do. So which will do, the phenyl, because migratory groups have to choose this, we know that, first hydrogen, then phenyl, then alkyl groups. So this phenyl group will going to migrate here. Okay, and this is going to be released. It means that what will get, this phenyl is there, and this migrate to this O, and here we have that CO minus, and here we have that CH3. Okay, now what will happen, that this will abstract from work of redo, then this will get the protons. So we are going to get this as the final product. Here we will have that O, and this is going to be, sorry, so not work up, so this is going to be O. Then what will happen? Yes, so this is going to migrate here, and this is CO, and CH3 is there. So what will happen? Yes. Okay, okay. So whenever it is shifted to, it will migrated to here. So that I already discussed that if any group is migrate, then this carbon will get the positive charge. That's what I said that, right? So if this group is migrating from here to here, then this group will get the positive charge. That's what I've discussed in pinnacle rearrangement, semi-pinnacle rearrangement. If any group is migrate, then that carbon get positive charge. So this carbon will get positive charge, and this negative and positive will make bond. So that you are going to get this as the final product. Or this is going to be the CO, because positive and negative make bond. Going to the, this is going to be the final product. Okay. So this is the mechanisms of the reactions. Okay, so you can do like this. This is the mechanisms of this Baeyer-Villiger oxidations. Or also this is also I did wrong here. Or also you can solve it by like it is whenever it migrates, then this is going to negative charge, because here we have that already positive charge is there. So that is neutralized. So that is going to be OH. And now what will happen that here OH is there. Okay, so OH is there. So this is get the positive charge. So now what will happen? These lone pair electrons will give it to this. So then also we will get that this things. Okay, so this way also the point. This is the mechanism of this reactions. Okay, so now this is the mechanism, but we always do the shortcuts to solve this Baeyer-Villiger oxidations. So what is the shortcuts here? What I will do? So yeah, I can solve here. So shortcut I can, how we will solve that? Shortcut is that wherever we will get these ketone groups, this, let's say this groups is there, CO and CH3 is there, and if we have that parasites, then what we will do that we will make this carbonyl groups. We will make that carbonyl groups, that always this carbonyl group will be intact. Now what we will do that here CH3 and this O is there. Okay, so now in between this we will check that migratory aptitudes. Here that migratory aptitude play very important roles. Now we will check that migratory aptitude between whatever I make these CO groups here as it is. Now I will check that other these groups and these groups in this group. So which is the more migratory aptitudes? So which is the more migratory aptitudes? So we know that migratory aptitudes, that is first hydrogen, then phenyl, then alkyl groups. So migratory aptitude is that phenyl. Okay, so phenyl and what will happen that which is the more migratory aptitude, in between that CO groups and migratory aptitude O will be come. So what it will come here? So I'm going to add that migratory aptitude in between that CO groups and migratory aptitude, whichever the more migratory groups, in between that O will come, and then that group will be there. It means whatever these groups, okay, and that remaining group is as it is. So this is the shortcut for the Baeyer-Villiger oxidations. What will happen that make these CO groups Okay, now check that migratory aptitude. Whichever is the more migratory groups, that in between that CO groups and that more migratory groups, that O will comes. After that, the other group will remain as it is. Okay, this is the shortcut for solving that Baeyer-Villiger oxidations. Okay, we will solve the examples, then we will be clear. Let's this example. So here what we see that in these groups CO is there. Now we'll check that migratory aptitudes. Which has the more migratory aptitude? CH3 and penile. So penile. So in between that CO and that more migratory groups, O will come here. It means that I can do here. This is the CO and the more migratory groups. In between what? O will come. So that is going to be the CO, and here O will comes after that. Okay, and the remaining group will be as it is. So this is the final product for this courses. If it is the Baeyer-Villiger oxidations, it means if meta-CPV is there and this is there. So what you do that insert the O. What I am doing here, insert O in between CO and more migratory group, migratory aptitude group. Okay, this is the very important for the Baeyer-Villiger oxidations. That we will do simply if the meta-CV is there. So we will check that migratory aptitude, which is the more migratory aptitude in between CO and more migratory aptitude, just insert the O groups. So same things we can do here. So here we have that CO. So here this is there and this is there. Means these CO groups adjacent are this carbon and this carbons. Now check that which is more migratory aptitudes. So about of that migratory aptitudes that I have told in the previous class also, that migratory aptitudes here in this Baeyer-Villiger oxidations, migratory aptitude play a very important roles. Okay, migratory aptitude, what I said that first hydrogens, then phenols, then alkyl groups, that we remember as Apur. Okay, now if it is let's say for alkyl groups, then first is 3-degree carbocations, then what I say that cyclohexane or cyclo groups, and then we have that 2-degree, then we have that 1-degree. Okay, and now if all are both are 2-degree, this is the 2-degree carbocations and this is also 2-degree carbocations. On that case, what we check that check which have more electron rich. So this is about of that migratory aptitudes. Okay, so this is the concepts about of that migratory aptitudes that we look in the BBO, Baeyer-Villiger oxidations. First, what we will see that first is that for the hydrogen penile and rings, first is hydrogen, then penile, then ring. If both are that alkyl groups, then 3-degree, then cyclo groups, then 2-degree, then 1-degree. Now, if both are the 2-degree, 1-degree, if both are 2-degree carbocation, or both are that 1-degree carbocation, or both are the 3-degree carbocations, then what we should check that check which is more electron rich. So likewise we will check the migratory aptitudes. Okay. Now for these questions, what you see that both are the alkyl groups. Okay, so we will check that which is the carbocations. So this is going to be the 2-degree carbocation and this is going to be the 3-degree carbocations. So what you see that 3 degrees more than 2 degrees, so O will be joined here. So that answers will be here, we will get O. Okay, so this is going to be the this is going to be the answers. It means that O will be inserted to the more migratory aptitude groups, means in between the CO and more migratory aptitude groups. Likewise, in this example also, how can solve with that? So this is going to be that here, what you see that this is also going to be the 3-degree carbohydrates, and this is also going to be the 3-degree carbohydrates. Then if both are the 3-degree or both are 2-degree and both are 1-degree, then what will check that? Check which have the more electron rich. So here we see that this is the electron withdrawing groups. It means that electron means it will take the electrons, it will abstract the electrons from here. So this is going to be the more electron rich, because it will taking electrons, this take electrons, so it decrease electrons for that. So that's why this is going to be more electron rich. So CO group will be at, so here both are the 3-degree carbohydrates, so O will be attached to this because this is going to be more electron rich. So answer will be, here we will get that O, this, and here we will have that CS3, here we will have that CS3, and here we will have that CH2 and NO2. So this is the final product for this questions. Okay, likewise we will solve that. And in this case, so what will happen that check that both are the penile rings. Okay, now if both are penile rings or both are the alkyl groups, we will check that which is more electron rich. So this is going to be that electron withdrawing groups. So now, so electron withdrawing group means this is the electron deficient. So this is going to be the electron rich. Okay, so what you see that both penile ring, then what will do? Check that electron rich groups. So that's O will be attached here. So answer will be AO, then this CO, then NO2. This is the final product. Okay, similarly here, so here both are the 2-degree, so and both are the same, so O can attach anywhere. So answer will be O we can add anywhere because both are the same. So we can write in this one. Okay, CO. So this is the final product. It means this 5-member ring, it is converted into the 6-member ring. So always you see that the ring expansion is happening in this case. Okay, this is the 6-member rings and it is converted into the 7-member rings. This is the 6-member and this is going to be the 7-member. Okay, because O is inserting in between that CO and the more migrating groups. Now in this example also we can solve that. Here what will happen, this is the penile rings and this is the alkyl group. So we know that first is hydrogen, then penile, then alkyl group. So O will be okay. So whenever you have that diketones, okay, whenever we have that diketones, on that time what happened, that insert O in middle of 2 ketone group. Okay, for diketones what is that, insert O in between the 2 ketone groups. So this is going to be CO, here O will come. Okay, in this case we will not check that this. So in case of diketones, this we have to keep in mind that in case of diketones what we will do, insert O in middle of the 2 ketone groups. 2 ketone group means in the middle we will put that O. Okay, so this is the final answers for these examples. Now looking for these examples, what is there? Here also that is very simple. We will add to this meta CPPBA. Okay, so we will check that this is the here, so which the this and this. So this is going to be the 3-degree carbohydrate and this is going to be the 2-degree carbohydrate. So the O will add in the middle of this. Okay, it means that O will be added here. Okay, so that is going to be like this. Okay, so that is going to be the like this. So over here 3-degree carbocation, so it will add to that. So in this case CO, this and this, so this is the 3-degree and this is the 2-degree, so O will be added here. Means O will be here, sorry, O, this one, and this is going to be like this, OMe. Okay, so that is added to the 3-degree carbohydrates. So in this also, here nothing is there, hydrogen, so O will be added. This is the 3-degree and this is the 2-degree, so O will be added here. Okay, so this is going to be the okay, and this is going to be like this. So similarly here, but now this is the very important. Now if here this is the 3-degree and this is the 2-degree, it's fine. But if 3-degree with that this type of highly steric hindrance is there, on that case steric factor will be dominate. Steric factor dominate the migratory aptitudes. Migratory aptitudes. What I mean here, it means that if this is highly steric hindrance, then what will happen, that this O will be not added here, O will be added here. Okay, it means that what will get this one, this is highly steric hindrance, then O will be added to the 2-degree instead of 3-degree. This is going to be the major product. Okay, and this is going to be the minor product. Although this is 3-degree, but here steric hindrance is there and steric factor dominate now. If it is highly steric factors, highly or highly steric hindrance, then steric factor dominates. Okay, likewise here we see that this is highly steric factors, although this is 2-degree 3-degree, but here that highly steric factor is there, so O will be added to this one. Okay, similarly moving to these examples, here also we see that this is 3-degree carbocation, this is 1-degree carbocation, but this is going to be this is 2-degree, but this is highly steric factor, so O will be added here, not there. Okay, similarly these examples, this is 2-degree and this is the 3-degree. 2-degree and this is the 3-degree, and this one last examples. So here what will happen in this case, this is going to be so 2-degree, so O should add here, but O will be adding here because here no much more steric hindrance, but still it will add here. That's we has to memorize. This is no concept is there, no concept. We should memorize this one. That in this case, that here is there. Okay, so here that is no much more steric hindrance, above is there. Okay, but still that O will added to 2-degree instead of 3-degree. Region is not explained because this is O will be added here. Okay, this is the answers. Why here? That this one has to memorize it. Okay, very important. This one has to memorize that if this type of group is there, in that groups here, that steric factor is here, above is steric factor is there, and this is 2 degree and this is 3 degree. So down there is no steric factors, so O should add it here, but again the O is adding to this one. So this is, there is no concept, it has to memorize it for this type of examples. But here, that here steric factor is there, that's why O is added to above, that's fine. But in this case steric factor is above, okay, down is no steric factor, so O should add here, because this is the 3 degree, 3 degree is more than 2 degrees, so O should add here. But again O is adding to that place, that regions that is not explained, and this one we should be memorized. So this is the last questions. So remember that whenever that groups is there in the above, steric factor is there and CO is here, then O will be added in the above instead of below. Okay, so these are all the questions related to Baeyer-Villiger oxidations, and we will solve other name reactions in the next class. So today up to this, thank you.